Computer scientists and mathematicians often generalize objects and code to make them more portable. It also helps to categorize objects and to make their usage more high level and defined. Abstraction layers are often created to help with these generalizations. Often, that means we need to identify objects that look or behave similarly, and if we look at their behavior and structure rather than their specifically named components, we may be able to draw equivalences that we could not before. This discussion will take us down an abstract road that may be difficult to comprehend at first. However, once you get the hang of it, you will see the beauty and the ability to simplify objects into something more manageable. Let's start by talking about isomorphic maps between groups. The word isomorphic comes from iso, meaning same, morphic, meaning shape. When two groups are isomorphic, they have the same structure even though they may look different. Drawing these connections between similarly shaped objects, or same-shaped objects to be more specific, allows us to reduce these complex objects into something more simple. In order to begin our discussion about isomorphic maps, we first have to talk about another map first. A homomorphism is a map between groups that preserves the operation. If we have a function f from g to h, then operation between a and b must behave similarly after the map has been applied. This is the essential property of a homomorphism. For example, the function that sends each integer to its remainder, modulo n, is a homomorphism from the set of integers over to integers modulo n. We'll demonstrate this later. Now that we have the notion of a homomorphism under our map, we can now hop over to an isomorphism. An isomorphism is effectively a bijective homomorphism. Bijective just simply means that it's both one-to-one and onto. Simply stated, every element gets maps to a unique element and nothing is left out. Bijective maps require that the original and resulting groups have the same number of elements. An isomorphism preserves the group operation while pairing every element of one group with exactly one element of the other group and nothing's left out on either side. When this happens, we say G is isomorphic to H, and we have a dedicated symbol to denote the relation. This will be demonstrated in examples shortly. Groups often appear different because they use different labels or elements. Some use numbers, some use letters, some use rotations, and some use matrices. Groups can be constructed with very complex elements. In many cases, the complex group can be shown to be equivalent up to isomorphism to a group with a very simple structure. We will call the two groups isomorphic. That means they are not identical or even the same group, but if we only care about the structure of the group and how they operate with each other, then we say they are equivalent up to isomorphism. We can think of this as ignoring labels and only looking at the shape of the group. This is very handy in reducing problems from the complex to the simple. Mathematicians use the benefit of isomorphic mapping to reduce complexity, as we mentioned earlier. When analyzing isomorphic groups, one group among the isomorphic collection of groups may have a format that's easier to represent in code or for an audience to comprehend. It becomes so second nature that even mature and well-versed mathematicians to incorrectly interchange representations. For example, cyclic group elements are usually represented symbolically with respect to the generator. Quotient groups elements are actually sets of objects where elements of the same set are considered equivalent to some definition of equivalence. The elements of the group of integers modulo n are just numbers from 0 to n minus 1. Despite knowing the different representations, mathematicians may interchange the representations in ways that may be abusive to the actual group definition. This can be difficult to comprehend, and I will provide some examples shortly. There are at least two aspects of isomorphic mappings that you should be aware. Identities always map to identities, and generators always map to generators. So even when mathematicians may slightly abusively interchange representations, for the most part, if they're talking to an audience that's well versed in the subject, it gets overlooked because it's usually a way of just condensing the discussion down a bit. Let me take a moment to pull up my notebook. I want to provide a few worked out examples and demonstrations for the topics that we have discussed. Earlier in my slideshow, I made a reference to three categories of groups, and I say for a given order, these three categories are isomorphic to each other. So I think that deserves a little bit of context, and I'm going to do my best to show that they are isomorphic to each other, but they are still very different groups in their representation of the elements. Okay, so those three groups were the cyclic group of order n, and we represent that with Cn. Then we have the integers modulo n that we represented like this. And then we had a quotient group, Z mod NZ. Now, the cyclic group is typically represented by an element that's just kind of symbolic. So sometimes we pick a number. So let's decide that we're going to create the, let's decide we're going to evaluate order 4 for each one of these. So we're going to look at C4, the integers modulo 4, and then Z mod 4Z. Let's give a concrete example here. So here we have 4 elements in a cyclic group. What is a cyclic group? A cyclic group is a group that's generated by one element. And what we're going to say is, I'll go ahead and leave this to you, all cyclic groups of a given order are isomorphic to each other. And that's not really all that impressive, because a cyclic group, whenever you actually represent its elements, you just pick an element G that's inside the group. So we'll just pick G. And we represent it this way. We have the identity element, which is effectively G added to itself 4 times. And so we say G to the 4th, which means the operation has been applied to G to itself 4 times. So anytime you take a generator and apply the operation to itself, the order of the group number of times, you end up with the identity. Then we have G itself, which could be represented as G to the 1st. And then we have G squared, which is effectively G plus G. And then G to the 3rd, which is G squared plus G, or G added to itself 3 times. Okay, so that is the classic way that we represent the cyclic groups. Now here in so these are the elements, the E, G, G2, G3, and that's all 4 of them. Now over here, what we do is we represent the elements 0, 1, 2, 3, and that's it. And we say that when you add 2 numbers, you just take mod 4, and then you kind of loop back around and you got it. Okay, so here, you're basically doing what this is prescribing. You're almost kind of doing that, except that you're not using numbers. And then over here, this is actually the hard one, because you're actually taking Z and you're partitioning Z into equivalence classes. And within an equivalence class, all the values are equivalent up to the modular value 4, up to that value mod 4. Okay, so let me go ahead and write out the Cayley table for these two, and then we'll move on to this quotient group. So the Cayley table, what do we have? We have E, G, G2, G3. Then here we have E, G, G2, G3. And we draw this out. Not a problem. So here, the identity, this is going to be easy. You just basically rewrite the elements. And then down this way, you do the exact same thing, because this is an abelian group, so that means the order doesn't matter, or the order of operands doesn't matter, and so the operation table is symmetric. So we have G3. Okay, now what does it mean to take G plus G? Well, that's just G2. What is G2 plus G? Well, that's just G3. What is G plus G3? That is just simply the identity. Now, what is G2 plus G? That's G3. G2 plus G2, that's G4. But let me take a look. I want to write something down. G4 is effectively what? G3 plus G. And what is G3 plus G? Well, G to the 4th is effectively the identity, so we could just write that here. And then G2 plus G3, this is probably where I should have wrote that, sorry. Jumped ahead of myself. G2 plus G3 is effectively G plus G plus G plus G plus G 5 times. Well, take a look at what this is. This is the identity plus G, and so this just becomes G. And so what is G plus G? Well, we're back at the identity. G, this, we already said this is G, and then G3 plus G3, that means that we have G2 by the same argument. So this is kind of the Cayley table of how you rewrite this symbolically. So the cyclic group is largely symbolic, where basically you take a generator, and it doesn't really matter what it is, it's just that you write it like this. And the cyclic groups are so easy to basically create that it's in a way almost so simplistic that people sometimes miss the point, right? Okay, so now let's go over to, so this was C4. I think I was saying C3. I'm sorry, guys. I meant C4. Now let's look at the integers mod 4. So we have 0, 1, 2, 3, and then we have 0, 1, 2, 3. And when we rope this off, kind of create an operation table here, notice that we have this identity element, and it goes down this way. And I'll quickly fill in this table. So this is just modular arithmetic. You add, then do mod 4. So we have 2, 3, 0, 3, 0, 1, and then 0, 1, 2. Now, notice that the mapping here is very simple, because if we just take the map phi of g to the n, that simply is mapped to n. So notice that these two Cayley tables are effectively the same thing with just different entries in them. Now this is very trivial because our mapping behaves like that. So when we say a homomorphic mapping, let me show you what that means. A homomorphic mapping effectively means that whenever we take phi of a plus b, this addition is happening in one group, and if we say it's equal phi of a plus phi of b, this operation is happening in the other group. Okay, so here's what we're going to say. We're going to say phi of e is 0, phi of g is 1, phi of g2, that's going to map to 2, and then phi of g3, that's going to map to 3. And so what that means is whenever I take phi of, let's suppose, g plus g2, that must equal phi of g plus phi of g2. Okay, so this is what it means to preserve a homomorphic mapping. So you take any pairwise elements, you have to have this established. Notice that this becomes phi of what? G plus g2, that becomes g3. Over here, what is phi of g? That becomes 1, plus what is phi of g2? That becomes 2. So phi of g3, by our mapping, this should be 3, and look what happens on the other side. We do modular arithmetic. 1 plus 2 is 3. Okay, well, let's make sure that we understand this maybe in a different way, with a different number, rather. Let's suppose that we say phi of g2 plus g3. Okay, that should preserve this, phi of g2 plus phi of g3. So what is phi of g2 plus g3? Well, that means that we have 5 g's added together, but 4 of them make the identity, so plus 1 more. The identity plus g becomes g. So this should become g, so phi of g. And this should equal, what is phi of g2? Well, this becomes 2 plus phi of g3, which is 3. 2 plus 5 is 5, or sorry, 2 plus 3 is 5. Mod 4 equals 1. And does it not say that this map holds true? So what that means is that for everything that you pick on the left-hand side, this map, for all the pairwise elements that you can pick from the mapping over here in this cyclic group, whenever it translates, it has to translate appropriately. That's what it means to be a homomorphic map. Now, whenever we say something is bijective, that just means that all of these elements get mapped exactly once to a unique element from over here. Everything is mapped and nothing is left out. So if you look, this is kind of a trivial map. I mean, this is a relatively simple map. So when we think about this, and we go back over to our cyclic group Cayley table, when we looked at this, this is almost so simplistic that people have a hard time digesting it, and they're like, what are we even looking at? Because this seems like strange. But then when you offer up this table, because everybody's familiar with modular arithmetic, it suddenly becomes very noticeable about what's happening. And so what we draw everybody's attention to is we say, well, C4 is isomorphic to what? The integers modulo 4. Well, this is kind of the canonical way of representing it, but sometimes people represent this Cayley table over here, and they will say, oh, that's the cyclic group of order 4. Not really. This representation means Z mod 4. This representation on the left where we have all the G's raised to powers, that's the cyclic group representation. Because there are actually matrices that could be cyclic group. There are integers that could be cyclic groups. All these things could actually happen, and we have to be really kind of cautious about how we represent elements. Okay, so C4 is isomorphic to C4, the cyclic group of order 4, is isomorphic to the integers mod 4. And we see that the two different representations, that if we pull ourselves away from the label and we abstract our mind away from the label, you see that all these G's can be translated to numbers, and the Cayley tables are effectively the exact same thing. Okay, so now I think I've got something that I need to help out with as far as understanding what this is. Z mod 4Z, for example. Okay, well, what this effectively is every element inside of Z mod 4Z, there's 4 elements, so it's going to be P0, P1, P2, and P3 are the elements. And the reason I'm selecting P is because they're going to be actual sets themselves. So the elements of this group are actually sets, but these sets form a partition of the set of integers. That means every integer will go into exactly one of these partitions. So let me go ahead and draw these out. So we have P0 is the values 0, 4, 8, ... And then we go backward, it will also be -4, -8, ... So what you want to see is that every value in this group is equivalent up to mod 4. So these are all the values that when you do mod 4, they become 0. Now P1, these are going to be all the integers such that when you take mod 4, you get a 1. So that means 1, what's the next one? 5. You just keep adding 4, so then we have 9, ... And then we're going to subtract 4, so we get -3. Subtract 4, we get -7, and then ... These are all the values that when you take mod 4, you get a remainder of 1. Then we have P2, and this becomes 2. Add 4, you get 6. Then you get 10, ... And then going backward, you get -2, and then -6, ... These are all the values, these are all the integers that when you do mod 4, you get the remainder of 2. And then for our last equivalence class, we have 3, and then we add 4, we get 7, add 4 more, we get 11, and these goes on to infinity. And then backward, we have -1, then we have -5, ... Okay, so these are the elements of Z mod 4Z, and you notice that they're actually sets. So this is definitely different, and then let's draw the Cayley table for this. We have P0, P1, P2, and P3. Then up here we have P0, P1, P2, and P3. And the way this operation works is take any element from one partition and add it to an element of another partition, and you should get another partition as a result. So let's practice. What happens if I take 5? What happens if I take 5 and then I take 10? I add those two together, so I take an element from P1, I take an element from P2, add them together, I get 15. But when I take mod 4, what number do I get? So I think if we notice, if we were to continue this out a little bit, we'd see that 15 is actually in this set. So if we take any element from P1 and we add any element from P2 to it, that will give us an element from P3. So look at how this operation works. We have P0, P1, P2, P3. Then we have down here P1, P2, P3, P0, P2, P3, P0, P1, P0, I'm sorry, P3, P0, P1, P2. So notice that this is a Cayley table. And remember, what is the operation? Take any element from one partition, add it to another element of another partition, you're going to get an element in another partition. And if you look, it looks like it maps directly to the integers modulo 0, because if you think about what the homomorphic mapping would look like, the map would be this. So you'd say Pi would just simply map to I. So this is an element from Z mod 4Z. Sorry, I need to do a better job writing this. So if we take an element from Z mod 4Z, and then we take an element from the integers modulo 4, what we say is phi of Pi would just simply map to the element I. Okay, and if we notice this, it will preserve this homomorphic mapping such that if I take Pi plus Pj, phi of Pi plus phi of Pj, we would see that this actually holds through, because what does this end up being? This end up being I plus j mod 4. And this over here ends up being Pi plus j mod 4, because that's how it effectively works. You'd find out that this actually becomes I plus j mod 4 is equal to I plus j mod 4. And so what we've essentially established is that the homomorphic mapping would hold through. And it's not even all that difficult. If I was to just rewrite this table using only the subscripts, that would effectively mean that I have the exact same Cayley table as what I had right here with the integers mod 4. And so what do we say? We say, I'm sorry, I went to the wrong one. We say that since we have a bijective map from C4 to the integers mod 4, these two are isomorphic. And we showed that the integers mod 4 were isomorphic to Z mod 4Z. By transitivity, it must be the case that C4 is isomorphic to Z mod 4Z. So the reason I wanted to run through that example is just to say, hey, look, this is actually something that's kind of nice. And so we have this transitive property, which is not all that surprising since we're talking about equivalence, but this one is almost so easily represented that it's almost like people kind of miss the point of it. This one takes a whole lot of work to describe and see what's happening, but this one, I mean, I'll draw it in green. This one seems to lend itself to code and something that everybody could digest. And so whenever you hear a mathematician talk about C4, they may actually represent it using Z4, and they may not even clarify that they're talking about an isomorphic mapping, because typically in an audience that's dealing with groups, one of the first things they learn is that all cyclic groups of a given order are isomorphic to each other, and a cyclic group of a given order is isomorphic to the Z mod n group, and then we could also say that it's a isomorphic to Z mod 4Z. So what a mathematician may say is C4 is equivalent to Z mod 4 is equivalent to the integers modulo 4 is equivalent to Z mod 4Z up to isomorphism. So maybe I put too many chain of comments there. What a mathematician may say, now these groups are different. They have different labels, but a mathematician may say C4 is equivalent to Z mod 4Z up to isomorphism. That means up to abstracting ourselves away from a label, they have the exact same structure. So I know that I've repeated myself a lot. I know that I have said this over and over, but it's really powerful because this one can be represented as one group, the Z modular 4 values. Very easy to digest. Now, let me show you something that may be a little bit less obvious. So I'll be up front. Whenever we wrote down C4 and we wrote down Z mod 4Z, it was kind of easy that the superscripts and the subscripts were just kind of basically Z4, and it really wasn't all that surprising. Well, let me show you another group that I've already done in another lecture. Let's suppose that I take these elements. I'm going to take matrix E, which is the identity, 1, 0, 0, 1, and I take the matrix, let's suppose G, notice that I'm actually picking this on purpose. This will be 0, negative 1, 1, and 0, and then we take G, when we say plus, we're actually going to say multiplication. So the operation plus is matrix multiplication. And so what happens when we multiply E times G? You just get G back, and that's not surprising at all. When you multiply these two things together, you effectively get 0, you get negative 1, 0, 0, negative 1. And then which is effectively the same thing as taking 0, negative 1, 1, 0, multiplying it by itself, 0, negative 1, 1, 0. You get this, and then when you take G3, which would be the same thing as taking G2, multiplying it by G, which would be negative 1, 0, 0, negative 1, times 0, negative 1, 1, 0, you end up getting this, which is almost similar to the other one, but it's 0, 1, negative 1, 0. And then when you take G4, which would be G3 times G, you get this 0, 1, negative 1, 0 times 0, negative 1, 1, 0. You multiply them together, you end up getting the identity matrix because you loop back around. So in this particular case, notice that I have effectively drawn the entire thing. We notice this is the identity, by the way. Notice that I have represented these matrices as a map to the cyclic group of order 4. You have the identity, you have G, G2, G3. I used one matrix to effectively generate them all. Notice that since I'm back at E, if I multiply G by E, I go back to this G matrix, multiply G to it, I end up G squared, multiply G again, I end up G third, multiply G again, I go back to the identity matrix, and I'll keep iterating through these same 4 elements, meaning that they were generated by a single element. And so what do we say these elements, the cyclic group of order 4? All cyclic groups of order 4 are isomorphic. So to be clear, this matrix and this G are not the same thing. And in one case, we had just a letter raised to an exponent. In another case, I actually have a matrix. So in this matrix group, the G and the matrix are 2 different representations, but we have shown that the matrix group is isomorphic to the cyclic group of order 4. Okay? So that's what it means to be isomorphic. You have a homomorphic mapping that is bijective. That means that the operation is preserved. Homomorphic mapping means the operation is preserved. And bijective means that everything is uniquely mapped and nothing has been left out. So that's effectively what isomorphism is. Now, in my opinion, imagine how long it would take. So I've taught these courses long enough that I know what these matrices multiply, but imagine you actually had to multiply these matrices. And you're like, oh my gosh, it takes a while to actually do matrix multiplication. So when you multiply them, you either have to do a lot of arithmetic in your head or you have to do a lot of writing. And so what we may say is, since we know that these matrices may form a group after we see it, maybe we used a computer to generate this, at that point, there's no real reason for me to keep representing this as matrices. Maybe I would just go over and represent these matrices as what? Maybe Z mod 4. So notice that this could actually be 0, and maybe we would call this element 1, and maybe we'd call this element 2, maybe we'd call this element 3. And so now we represent this as a matrix group, but we said that it's actually the cyclic group of order 4 up to isomorphism. And then, well, we might as well just represent this in code, so that way the arithmetic will be much easier. Instead of having a computer calculate all these matrix operations, we just have it do Z mod 4 operations, which would be a lot less expensive. Okay, so now you see, even in code, even in mathematics, this notion of isomorphic mappings can actually make us a lot faster. It actually makes things a lot more digestible and easier to comprehend. So that's the idea. We take complex objects, we kind of boil down their structure, and we abstract ourselves away from the labels, and then suddenly we end up with a group that's very familiar to us, and we can use it much easier in code or our representations. So thank you. That is the power of isomorphic mappings. Let me take a moment to summarize what we just discussed. Isomorphic simply means same shape. We take a bijective homomorphism, and that means if we can establish that map, two groups are effectively the same up to their structure and their behavior as far as an operation. It's like we're abstracting ourselves away from the labels. So, even though groups may look different, and one group may be very complex and the other one very simple, it may be the case that they are actually equivalent up to an isomorphic mapping. And in such a case, it allows mathematicians, computer scientists, or any other scientists making the conclusions able to use a group with a much more simple representation to effectively achieve the same thing. So again, this is a lot to digest, and it takes a while to get used to the nature of isomorphic mappings. All right, thank you for watching this lecture. I hope that you found it helpful. I hope that you found it insightful. Please leave comments and anything that you want to share about how I can improve in future lectures. I do read those comments, and I do try to incorporate them into lectures to help you learn. So until next time, see you around.